Welcome to this presentation of our work on semi-supervised learning with scarce annotations. In this presentation we are interested in the task of semi-supervised learning. In this scenario we consider a dataset with few annotated samples and lots of unlabeled ones. This task is generally more suited for real-life scenarios since unlabeled data is abundant while annotations may require extensive work. This work is particularly interested in the limit where the labeled data are extremely scarce. Prior work such as Mean Teacher generally uses an efficient teacher-student model where both models are trying to minimize a consistency loss between a data point and its transformed version. However, this pipeline isn't well suited when the labeled data become very scarce. In this work we try to leverage this limitation by proposing an efficient two-steps algorithm. First, we pre-train our network on all data using self-supervised learning to obtain a first efficient initialization. In this work we used the RotNet self-supervised method. Our second step is an alternative optimization algorithm where we alternatively optimize our network on the labeled set and the entire set. Between these two phases the information flow through soft constraints, namely pseudo-labeling and weight freezing. After the first self-supervised training step we replace the classifying head by one adapted to the number of classes in our dataset. Then we freeze the first two blocks of our network and train a cross-entropy loss on the labeled set only. During phase 2 we start training on the entire dataset which comprises the labeled and unlabeled data. To this end we produce pseudo-labels on the unlabeled data extracted at the end of the first phase. Then we minimize our objective loss which is a weighted average of a cross-entropy loss for classification and a consistency loss used in traditional semi-supervised learning pipeline. To further avoid overfitting we held out 1/3 of the unlabeled data during this phase. Then we resume phase 1 by training on the labeled set again. But from then on we only train the final linear layer of the network in phase 1. And after this phase proceed to phase 2 again and keep alternating until the end of training. Our results show that our method is at par with Mean Teacher algorithm when using self-supervision as network initialization. Besides, self-supervision is shown to be very effective in all cases when labeled data is scarce. Our method can also be combined with other algorithm. When combined with Mean Teacher our method reaches state-of-the-art performances, on various datasets. In fact our method works increasingly better with good initialization. We show that when using an upper bound pre-trained ImageNet initialization, our method is reaching state-of-the-art performances on different datasets, beating all competitors. This further demonstrates that our method works increasingly well with better initial representation. Finally, our work does not rely on one type of network architecture. Similar performances can be obtained with deep models found in the literature. On an opening remark we note that while self-supervision methods are ranked by how well they perform on supervised tasks, semi-supervised learning could also be used to rank such method. Thank you for your attention.